Welcome back to Maths 530. This is lecture 12, and as I already said, this one will be on Zoom. So my plan today is to go into more details on tournaments and their Hamiltonian pairs and a few other things about them. This is not a mainstream topic in graph theory. It's a pretty useful topic for certain things, but you can have a graph theory class where the word tournament doesn't ever fall. Nevertheless, I find it an interesting thing to discuss. So I have everything I'm doing today is done in more detail in my notes for spring 2017, which I've just updated a few weeks ago. So these notes are not actually written in 2017, but I will be more terser today. So let me recall what a tournament is. It is a loopless digraph with a certain property. Loopless means it has no loop. Digraph means that arcs are directed. The certain property is the tournament axiom. It says that for any two distinct vertices, there is either an arc from one to the other or an arc from the other to the one, but not both at the same time. So for example, here is a tournament with 5 vertices. If you forget about the arrows, you just see a complete graph K5. And that's the idea of a tournament. It's basically a complete graph with every edge being directed. So let me spell this out. So a tournament can be viewed as a complete graph whose each edge has been given a direction. And you can choose those directions freely, but you cannot direct an edge both ways at the same time. So before I get started with anything substantial, let me again restate the definition a little bit. This will come useful using the following notions. I think I did this in lecture 11. Let D V equals VA be a simple digraph. Then we define the digraph D rev. This is pronounced D reverse, and this is again a simple digraph to be VA rev, where A rev is just the set of the reversals of all the arcs in A. So for any arc UV in A, you have the arc VU. This basically means you take each arrow and turn it around. Same endpoints, but the source is now the target, and the target is the source. And next, we define the simple graph D bar, simple digraph D bar, to be VA bar, where A bar is the set of all pairs U, V of two vertices that are not arcs. So basically everything that could be an arc and but is not an arc now becomes an arc, and all the original arcs get forgotten. This is called the complement of the digraph. And of course I can rewrite this in a slicker way. I can just say V cross V without A. And now here is an alternative description of a tournament. It is basically saying, let D V equals VA be a loopless simple digraph, then D is a tournament if and only if the arcs, the non-loop arcs of D bar are precisely the arcs of D rev. And this is just a matter of looking at the definition and rewriting it in this language. So basically a missing arc here is actually a reversal of an existing arc. So back in lecture 11, we stated a couple theorems. Lecture 11 or lecture 12? Lecture 11. So the so-called easy Raday theorem, easy and hard is my nomenclature, but the easy one is saying that any tournament has at least one hemp. Recall, hemp means Hamiltonian pairs. And the hard one says that any tournament has an odd number of hemps. And of course, the hard one implies the easy one, because an odd number is always non-zero. So there are a few things we can do. We could actually prove the easy theorem. It's called easy for a reason, and there is pretty simple proof in the notes. But that would be a waste of time, because I want to prove the hard one. And if the hard one is proved, the easy one follows. So let me get to the hard one. So we recall, or we recall a result from lecture 11. This was a result. I call it Birch's theorem. I mean, Birch has many theorems. It's one of them, saying that if D equals VA is a simple digraph, then the number of hemps of D bar of the complement is congruent to the number of hemps of D mod 2. This is actually a pretty complicated thing to prove. It took us a while. We had to argue with all sorts of unexpected things. We have this V-listing, arc set, pass covers, and somehow everything came out correct in the end. It was quite a surprising argument. And also, a much simpler result is that this is true for the reversal. And this is not just a congruence, this is just an equality, because you can just turn the Hamiltonian pairs around. So how do we prove the Hartree-Day theorem from this? And this argument itself is not quite trivial. It's also nice. So let me make some preparations for it first.